Hello and welcome to another Energis AI tutorial. In this short video, we're going to be looking at running the energy efficiency of a house and the heating and cooling requirements. So here on the UC Irvine Machine Learning Repository, there's this data set for energy efficiency, and this study looks into assessing the heat load and cooling requirements for buildings as a result of the building parameters. So they perform energy analysis using 12 different building shapes in Ecotect, which is a product through Autodesk, an analysis for architecture or civil engineering, where they simulated various settings as functions of some characteristics such as the glazing area, which is the area with windows, the orientation, as well as the wall perimeters and other things. Uh, so they've come up with 768 samples based off of these 8 features, and they want to predict real valued responses without actually having to go through the whole analysis process. So out of the 678 or 768 building shapes, there might actually be 1,500 building shapes, for example, that they would want to solve for. So taking this data set, we can open it up and transfer it over to a CSV file. We can see they already formatted it pretty well for us off the bat with all of our inputs and outputs. The first 8 inputs here are the relative compactness, the surface area, the wall area, the roof area, the overall height, the orientation, the glazing area, and the glazing distribution. So out of these, the orientation would have been predefined by the user. So say they have a specific shape that they're using for their house, and they're just identifying which shape configuration they're using by either 2, 3, 4, or 5. Same with the glazing distribution. So where the windows are located on the house, in their program, they would have had a set number given for each configuration. So to set up our inputs and outputs file, what I'm going to do is I'm going to cut these 2 last rows, and I'm going to take these and put these into a new spreadsheet. So I'll just copy and paste those, and I will save this as our outputs. So this would be heating outputs. We're going to save that as a .csv file. Now that that's saved, we can open up our AINet platform. I've already got it loaded up with the model that we're going to use. So just for reference, we're going to be using the advanced very small numerical model, and we're going to be using it with 10 input nodes because we only have 8, and we're going to run it for 20 iterations because I've never actually run this data set before, and we're going to say about 50 nodes. So here in our AINet platform, we're going to set this over to a linear loss function because I noted some of the results might have 0. We have 1 input data header, we have 1 output data header, and we'll just select our input data, which is our heating outputs.csv. I'm just going to double check that I actually saved it with the removed rows. Our power requirements.csv is our inputs, and verifying that this is saved. Our output is heating outputs. And we'll submit our model to the server, and we'll revisit it once this has been returned back to us in the active state. So now that the model is in the active state, we can open up the active model menu in the AINet program. We can go over to our model metrics. We can see that it came up with a 21 first layer nodes with a ReLU transfer function and 0 nodes on the second layer and on the third layer. I actually went back before this completed training and switched it over to a relative loss function rather than a linear loss function, just because there was no zeros in the output data, and due to the variance in the outputs, whether it goes from 14 up to 100. So plus or minus 10 is not so bad on 100, but plus or minus 10 is pretty bad on a 10. So we can see here this model came up with a plus or minus 8.04% accuracy. And our model history here, we can see that it took about 14 minutes from start to finish training. So we can go through here, we can select 1 input data header, we can put in our original data file, and we can select the same output location, and we can run our results here. So here in a matter of about 2 seconds, we can run a quick analysis with plus or minus 8% accuracy to get the heating or cooling requirements of a home based on some basic input data, uh, rather than running a full simulation through a software and modeling up the whole house. That concludes the analysis of the provided data with the heating and cooling requirements of the house. But before we close out this video, I just want to go through a few other points that we could use to potentially improve our model and its utility. So here in our inputs, we have the relative compactness, the surface wall area, the wall area, the roof area, the overall height, the orientation, the glazing area, and the glazing distribution. To get a little bit more utility out of it, we could also include things such as the insulation values, the panes of glass, the latitude, the longitude of the house, as well as different shapes, how many stories there is, and then even the heating type, whether it's electric, gas, otherwise. And all of this information could provide more context toward our AI to provide a better picture and potentially use it in more areas. Because with the default data that they have here, they're limiting themselves essentially to one area with one specific type of insulation, for example. So just improving the generalization of your AI. And with that, I'm going to close out this video. Please like and subscribe this video for more content like this. And good luck on your future AI projects.